Happy Friday to you. I hope your midterms are going well so far. Yeah, some mixed responses. Today we're starting a new method, which is going to be our last of the velocity/acceleration analysis methods that we learn in the course. This is the last topic on the midterm, as I mentioned before, is finished now. Velocity and acceleration polygons. So the last material for that would have been the tutorial this morning, which covered the more advanced problem for acceleration polygons. And you're working on the problem set, which is about that topic. And the due date gives us time to give it back with enough time so you can review that in advance of our new date, November 5th, for the midterm, late date. So our new topic is not going to be on the midterm, but the final exam is going to be, highly likely. The final exam will be cumulative, but you'll be more likely to see topics that weren't covered on the midterm, of course, on the final exam. And vector loop method, a lot of you have been anticipating this method, and especially for your projects. You've been basically asking me, how can we do a full mechanism analysis that's not just a snapshot? So these first two methods are just for a snapshot in time. Right? We isolate one mechanism configuration where link 2 is right here, and we study it. But those methods are not good for finding things like max velocity points. They're not good for drawing out path of a point over the entire motion. They're not good for finding where links are going to break due to fast acceleration later on, because they're kind of manual methods, right? So our last method is going to address all of that. It's our most powerful method, so we'll call it a general method, meaning you can calculate for the whole rotation of the crank input or whatever the input is, the whole cycle of motion. We're going to have an equation that describes whatever we want. So we're going to have position, velocity, acceleration equations, whatever you want, we can calculate it. So we're getting more powerful or more capable as we go here. And you may wonder why we did the earlier methods. Why don't we just skip to the equations? And because as we go through these, I think that the methods get less intuitive, and they tell you less at a glance about what's happening. So remember, our instance centers method was very, very basic. We're thinking about motions between links, and there were lots of mental images we could draw from our mechanism motion. So as we go down, we're going to be getting less and less intuition from the methods. In the output instance centers, right, we get all that. We have to go through all the steps and visualizing individual links. So it tells you a lot about how the mechanism is moving, and you can visualize motions. Velocity and acceleration polygons is another way of visualizing motions. You see velocities right there on your polygon. You see accelerations drawn out as vectors. So it's a very graphical, very physically meaningful kind of way of laying everything out. Vector loops, on the other hand, we're going to get some huge equations, and they're going to be really big sometimes. A bunch of sines and cosines, this big mess. And you're going to look at it and you're just going to say, okay, unless I plug some numbers in and calculate or do something in MATLAB, it's really hard to know anything about my mechanism from that. So all these methods they complement each other, different strengths. And so one of the big things for your design projects, I'd like you to be thinking, for this section of methods more than anything else in the course, you have multiple options, and I'd like you to think, what's the purpose of my analysis? If I know where my limit position is, and I want to calculate acceleration of some point at the limit position, probably you should choose method 2. That would be a great way of doing that in a visual way. If you need to plot out something that moves over its entire motion cycle, probably you're going to use vector loops, and you're going to plug them into MATLAB, and you're going to do some additional analysis, just like you do in the labs, the practical labs. Instance centers. Would you use instance centers for your project? Maybe. Velocity acceleration polygons you probably find them more powerful and more logical to use for real problems. So I would say instance centers are going to excel when you want to learn more about a mechanism. And so that's more of an internal tool that you can use. but you likely will gravitate to the more powerful techniques for doing real analysis of real mechanisms. Any questions about our overall layout here? We'll get into our equations. Okay, so if I told you, I want you to describe mechanism motion using some equations, right? And I gave you a slider crank mechanism. I think you could figure it out. And I said, I want you to calculate velocity of the output as a function of the input. And I just put that on the midterm and gave you lots of time to figure it out. I think you could do it. You could draw up some trigonometry, right? You could define some angles and lengths, and you could calculate it, right? All our mechanisms it's just geometry. Trigonometry, you could define positions and then take some time derivatives, right? And that's always going to work. You can do that for any mechanism. But what I'm going to teach you now is more of a standardized approach to laying out a bunch of vectors that are going to generate equations for us in a standardized way that's going to allow you to solve any mechanism, no matter how complex it is. We're going to have this way of doing it. And we're going to be dealing with positions, velocity, acceleration. Okay, and we're going to get equations for each of these. Equations for each of them. So we're going to start with positions. Then we're going to take time derivatives to get velocity and acceleration. So we're going to set up a way of drawing loops of vectors, is what it's going to be, that are position vectors. We're going to start here, and then we've reduced our problem just to math. It's just going to be position equations, and we just deal with time derivatives then, which are not fun to do, but you'll get good at it because they all look the same. And you can plot these out. So we could plot something like position. Let's say we have some input, x1. We want to calculate some velocity output. And you'll be able to plot these out using some software, MATLAB. Or you could do things like if you want to find a position where max velocity occurs, you can use your mathematical tools. If we have an equation for velocity equals, you can use whatever mathematical tools to analyze these. Take its derivative and set it equal to 0. That's where velocity is going to be max or min. Right? So these are going to be powerful equations. Whatever you want, accelerations, velocities, you can plot out multiple things. And so that's what we're going to do. So we're going to start with this standardized way of drawing vectors. And we've drawn a lot of vectors before, and I tried to use the standard. I didn't fully explain it maybe. Okay, and you don't have to use this standard definition of a vector, but if you don't, you're probably going to make a lot more errors. So I suggest that you try this out. So we're going to express the position of this point A relative to the ground. We'll call that point O there. You could think about it like a base pivot or point on your mechanism, something like that. And starting with this method, vector loops, we're going to use, for position vectors, we're going to use capital R for position vector. Okay, so we're going to have a position vector of A relative to the ground. And that'll be R, and we'll number them in our mechanisms. For example, if this was lying along link 2, we'd probably call this R2. But you can name them whatever you want. And we can parameterize or describe this vector using xy coordinates or angles and length. And unlike everything we've done up till now, which used radial transverse coordinates, we're going to use xy Cartesian coordinates. Right, the value of radial transverse coordinates is that it allows you to study things like sliders and isolate the sliding motion. And it's all that case 1 and case 2. And that's really valuable for thinking about motions of links. But this method that we're going to learn is more general. So we're not going to think so deeply about the mechanism motions. And instead, we're going to have a really generic vector description with x and y Cartesian coordinates. You can think about like an I unit vector in the x direction and a j unit vector in the y direction. So if we have our angle of our vector theta, then we can divide this into its x and y components. Okay, so I'm going to write out several ways that we can write our vector here. And these are really standard: xi plus yj. Or we can use the angle. Yeah, we can use the angle. So we could have x is the same as r cosine theta. Right? So that's another way we could write it out, where r is the length of our vector. Lowercase r is the scalar length. And once we put it into a vector, we're going to call that capital R, and we'll put a vector sign underneath it. Okay, so this is another way we can write this out. And these are often going to be written in like a matrix style format. So another way we could write these is put them into a vector, like a column vector like this, where it's implied that the first column is x coordinates and the second column is y coordinates. So we can write out like this. And this is going to be a common way that we're going to describe these. And I'm going to use a little bit of even shorter notation for cosine. We're going to be writing cosine and sine hundreds of times. So I'm going to write cosine as c and sine as s. Tangent will be t. Okay, from context you can figure that out. If there's a c theta, that means cosine theta. Okay, so this is our standard vector, and really there's something very important in what we've done here is how we define that angle. So our standard theta, our standard angle, right, in this right here, our cosine theta, we assumed that the angle is defined with respect to the horizontal there, right? If you defined it like angle down from the vertical, you'd need to switch these and put some negative signs. So baked into this definition, we assume that the theta is measured up from the horizontal. Okay, it's from like the right horizontal, which I call the east. Okay, that's not like, you don't have to use that definition, but if you use a different definition of theta, you have to rethink your r vector definition. And we're going to do this over and over again. And you're going to see that our method, we're going to call it loop method. We're going to put these vector loops going sequentially around our mechanism. And it's going to be r plus r plus r plus r plus r. And if you keep a standardized definition, you can keep track of everything and not have to redefine it for every single angle. So that's how we're going to do it here. Okay, what else do we know about this? If we want to calculate theta given x and y, of course we can use our tangent. So it's going to be equal to y over x. So if we want to solve for theta, you can use an inverse tangent. Solve for theta. And that's fine to do, and that's something we're going to do a lot. We're going to write out these expressions. We're going to solve for x, y, or theta. If you want to solve for theta, you can use inverse tangent. The problem with doing this is that inverse tangent fails half the time. Fails half the time. Basically, you can imagine it can't differentiate between quadrant 1 and quadrant 3. If x and y are both positive, it's quadrant 1 like this. If x and y are both negative, and r is down here, you get a negative divided by a negative, which looks the same as quadrant 1. So inverse tangent is kind of a flawed tool. It's a flawed tool. It only works for quadrant basically like 1 and 4. If you're in quadrant 2 or 3, which is like northwest and southwest quadrants, you need to add 180 degrees. 180 degrees. So you see people write this as like adding pi radians times k, where k can be 0 or 1, to kind of correct your inverse tangent. It's all kind of difficult to handle. You kind of have to test it out to make sure you're doing it right. The good news is you should just never use inverse tangent. There's another function which is written into like programming languages called atan2. Arctangent 2.0. And instead of feeding it this y divided by x, where you lose the signs, instead of feeding it as one, passing it as one calculated value, you pass separate values for y and x. Okay, so in programming languages, this is going to be the way to get it. So it's implemented, or you could imagine writing one with, it basically does this correction for you. Okay, so this is what we're going to do. This is our basic setup. The last thing that I'll mention is that the textbook uses an alternate notation sometimes. So if you're looking at the text, they represent vectors using complex numbers like I, imaginary numbers. And in the book, this is Appendix B. They explain all this. You can check this out. And if you read books or research papers about mechanisms, you'll often see this used, which is why the textbook uses it. So instead of describing things with x and y and I and j directions, they work on this complex plane. So here's our R vector, where the horizontal axis is called the real axis. And the vertical axis is the imaginary axis. Okay, and really what this is doing is it's exploiting the fact that imaginary numbers like I, imaginary number I, can keep track of two quantities for you, a real part and an imaginary part. So it's pretty handy for dealing with planar geometric problems like this. So you would write the position vector now as x plus I, y, where I is the imaginary number, square root of -1. Okay, so this is just like a way of keeping track of things, or you could rewrite this r, x is cosine, right? Cosine theta plus I sine theta. So it's just a way of keeping track of things, but it also has this cool property. Imaginary numbers, you'll recall, you can rewrite sines and cosines, if you lay things out like this, using something called Euler's formula. You can rewrite this as RE to the I theta. This is called Euler's formula. So this is pretty cool. It's like a really compact way of describing these position vectors. And if you do any advanced study on mechanism design or things like robotics, describing the position of robotic manipulators, using this notation style unlocks some mathematical techniques using imaginary numbers and things that you can use. So at any rate, I introduced it. I'm not going to use this notation, imaginary or complex number notation, but the book does. You'll see some examples done with this. You can easily convert between them back and forth. We're not going to really use for this course that doesn't get into the really sophisticated uses. It's just like another notation style. Okay, so this is our other way of representing things. So now I'm going to introduce, let's actually use these. This is all pretty basic so far. We're going to start our vector loops. Okay, and we're going to basically attach a bunch of vectors to our mechanism. And we're going to write vector equations. Okay, so we're going to sum up a bunch of vectors into an equation. Okay, and these need to describe the mechanism motion. So we're going to choose what vectors to do to put on our mechanism. So we're going to choose vectors which capture all of the mechanism motion. And I'll show you some examples in the second half of today. Okay, it captures it, meaning every piece of the mechanism needs to be attached to one of our vectors somehow. If something's moving and it's not incorporated into our equation, it means our equation is not capturing the entire effect of the mechanism. Okay, so we're going to do this thing called loops. Loops. And this is not the only way of starting and drawing, putting vectors on a mechanism, but it's a nice standardized way, and it's the only way that we're going to do in this course, where we're going to start at any point on the mechanism. Okay, you can start anywhere you want on the mechanism. It doesn't matter. You likely want to choose a base point, but you can start anywhere. And then you're going to go around the mechanism and sequentially add vectors. Okay, sequentially meaning one after the other. So that means like head to tail or head to head, it doesn't matter, but they need to be sequential, one connected to the next, so that you can add them, right? So something like R1, R2, and we call it a loop. This is our loop method because we're going to always define them to come back to the beginning. So I'm just making up one for a simple mechanism here. It's going to form a loop. So the loop needs to close. So it closes back to the starting point. Okay, and the important thing about that, or why that is a condition, is that that's going to allow us to write an equation which is set equal to 0. So our vector loop for this loop is going to be R1 plus R2 plus R3 equals 0. And so that's every vector loop we write is going to be that way. Sum up all your vectors, although some will have negative signs later, as we'll see. Sum them up and set it equal to 0. Your loop comes back to where it starts. So it started here, went around, and came back, so we know that it should equal to 0 if we add all those up. I'll put one note here. We may need more than one loop. So that's just a note you can put there for now, and we'll investigate that next week, how you can identify when you need it. And we're going to have a really systematic way of going through this. We're going to have basically a test that'll tell us when we need one loop or multiple loops to describe what's happening in our mechanism. So I'm going to give you an example now. We're just going to look at a 4-bar. I'm going to draw it. We're not going to do anything that precise here. We're just doing the example of how to describe this mechanism using vectors as a loop. Okay, so this is our vector loop, and I'm just going to use another color so it stays a little less cluttered. We're going to attach a vector to each link, and we're going to capture the key points. So we have these points up here. Clearly, we should have vectors ending or starting at those points at all 4 of the pivots. So this mechanism, clearly we're just going to have one vector going each one, and they're going to be attached to the links. So this is our first vector that we're going to add, and we're going to call it R2. Then we'll just keep going around. R3. We'll go down link 4, and we need to come back to the beginning. And you can name them whatever you want. Choose something logical when you can. I'll call the last one R1. And so our vector loop equation's going to be R2 plus R3 plus R4 plus R1 equals 0. That's our vector loop. And I'm actually going to sketch out the loop separately over here. And we're going to put our angles on it just to make sure we know how this is done. And we're going to see how we have some choices with how we define our vectors. Okay, so I'm just going to put the vectors over here. And if you're solving problems, you can do it on the diagram if it's not too cluttered, or you may have to do it separate. Okay, we're putting it here so we can put the angles on and make sure we know what's going on here. So thinking about our definition of angles, it's covered up here, but our definition of angles, we always start from the east, from the right horizontal, and we go counterclockwise up to the vector. So let's put on each angle. And so each vector is going to have an angle to it. R2 is going to have an angle theta 2. So look at the base of the vector, not the head, the base, and go up from the horizontal. R3, start at the base here. Very good. Now R4, the base is up here. And so R4 actually has a big angle. So we start with the east direction. So theta 4 is like a 300 degrees there. And theta 1, (180 degrees). Okay, and all these angles can change over time, except for theta 1 is fixed, right? So we'll say theta 1 is constant, 180 degrees. But we have 4 variables here. One of them is set constant. And this is our equation. And in reality, we're going to see this is 2 equations. Hidden in here, there's 2 equations. It's a vector equation, so we can write it as 1. But really, there's an x and a y equation. So we're going to have all the x components sum to 0, all the y components sum to 0. And that's how we can, we're going to divide this and use it as a usable equation. Now, when we look at this, we see some of these angles are really big and cluttered. I'm going to show you a second way of drawing the loop for this mechanism, which is equally valid. So we're going to have a choice. So this is my second, take 2. A second option. There's lots of options. You can choose to put them in different ways. Or you can think about this like an alternate. So here I'm going to go R2 plus R3. But now I'm going to reverse the direction of the next 2 vectors. So I'm going to call those R4 prime and R1 prime, just so we can keep track. It's different. They're opposite from above. Okay, this is equally valid alternate loop. And why would you do this? So these angles are nice and small. When I do it this way, it's easier to define the angle on here. So it leads to a little more compact drawings, and theta 1 equals 0 in this case, constant. Okay, so I don't know if that's a strong reason for choosing this drawing over that one. It's a little bit less cluttered, putting my angle definitions on there. It doesn't matter so much, but what if you're given an angle ahead of time as a definition? Like I give you a problem, and I define theta 3 like this for you. It'd be nice to use that theta 3. So putting, it should be 4, right? Yeah. It'd be nice to use the same angle that I give you as a definition. So this way you can choose your vectors to go positive or negative and just add 180 degrees to your angle. And what does it happen to our loop? We started our loop here. We went around clockwise. So I'm going to write my loop equation here. So we started with R2. So anytime we go with a vector, we're going to go around the loop counterclockwise and write our loop equation. Anytime we go with a vector, tail to head, it's going to be positive. So R2 plus R3. But now we're going to go backwards down R4. So anytime we go from head to tail, we're going to subtract that one. And same thing for R1. Okay, both equations are valid, both loops are valid. They have different theta definitions, but otherwise they're the same and they describe the same motion. And if you wrote these out using sines and cosines, you'd see that theta 4 prime is like theta 4 minus 180 degrees, right? So it's like switching a sine to a cosine. It's all handled for you, right? Just use your standard definitions, define them how you want, and add the signs on appropriately, pluses and negatives. Any questions about our loop formation? Yeah.
Is it wrong to keep all your vectors clockwise, but just use like a negative angle? Like making theta for, in say the first example, 60 or 70, or sorry, theta 3. Theta 4.
Okay, so you're saying, what if we defined a different theta that was like
Negative 70 or something like that for theta 4.
you talking about this one here, theta, the prime version, or
No, the first one.
the first one?
Point the same direction, but anytime you have a theta more than 180 degrees, you just do negative.
So yeah, negative angles would be going around this way.
Yeah.
So yeah, positive 180 is the same as negative 180. That one's trivial. But if it was like this one, positive 100, you could call that a negative the other direction. It'd be like a negative 250. That you can also describe it, but positive direction is like you're going around counterclockwise from that way. It's all just in this x equals r cosine theta, right? So this is what defines the angle. So whatever works with this, you need to make sure that your angle works with that. So thinking about negative angles and whatnot, you can test it out and make sure that that still applies. I don't know if that addresses your point. Other questions about our loop formation? Okay, so you choose the loops, right? You choose the loops. I chose to add a vector to each link. You could make up another loop. You could make up a loop that starts here at O2 and comes here to this point D, down to O4 and back. That's not a wrong loop, but the vector going across here isn't attached to anything. So it's not going to describe anything about your mechanism. It's not going to capture the motion of link 2 and 3. It would only capture the motion of link 4. See, there's infinite number of loops that you could invent to put on this mechanism, but only certain loops will be useful for you. This one captures the motion because it captures these angles like theta 2 and theta 4 and the length of the links. So usually you're going to identify all your key points and then just connect them with a bunch of vectors. Okay, so the next thing we're going to think about is how do we know when a problem is solvable? We're going to get these vector loop equations and we're going to try and solve them. So we're going to think a lot about which variables we use to describe our mechanism motion. We're going to count them up and we're going to classify them as known or unknowns. And this is the most powerful part of the vector loop method, is that you can follow it systematically and make sure that you have a solvable equation and you know that you'll be able to calculate what you need. So we're going to always think about the variables in the problem, or the parameters. And these are going to be, for this problem, right, the things that vary are the angles. Okay, we also work with velocities, rotation rates, for example. But time derivatives are not going to count as variables. So we're going to say theta 2 dot, that doesn't count as a variable. That's a time derivative of a variable. And this is going to be important because we're going to be counting up our variables, and we're going to see that each loop is going to allow us to solve for 2 unknowns. So for this problem, we know that a 4-bar mechanism has mobility 1. If you put 1 input on it, like we set theta 2 as an input, we should be able to calculate everything else, like theta 3 and theta 4. So each loop is going to allow us to calculate 2 variables, so we need to be able to count them up correctly. Time derivatives of variables are not variables themselves. Okay, other mechanisms will have sliders, and those will have R as variables. Okay, so like the length of each vector can be another variable for other mechanisms. This one, all of the lengths of these are constant, right? They're attached to solid links. So for this particular mechanism, our lengths, lowercase r, are not going to be variables that are changing. For example, a slider crank, we'd see these. Okay, so our variables, these are going to choose or define the state of the mechanism. Okay, and the goal of our analytical study is to solve for the unknowns. So the goal of this whole method, vector loop method, is to solve for unknown variables as a function of inputs, the known ones. Okay, so we're going to have known variables, theta 2, for example, you might know as an input. And we're going to have special names for these in vector loop method. So I'm going to define these names for you. They should make some sense to you. We're going to call them dependent variables that depend on the inputs, and independent, which you choose yourself. Dependent. So dependent variables, these are going to be your unknowns. Unknowns. Okay, so dependent variables is the term that we're going to use. We'll often call them DV for dependent variables. Okay, for our problem, for this 4-bar mechanism, the unknowns would be, if we put theta 2 as the input, the unknowns would be theta 3 and theta 4. And as I mentioned just a minute ago, each loop will allow us to solve for 2 dependent variables. So this is going to be our check. We're going to count up all of the unknown variables in our mechanism. And we're going to say, how many are there? This problem has 2. And that's going to tell us that one loop, which we defined for our mechanism, one loop, is going to be able to solve for both if we choose an appropriate loop that captures everything about our mechanism. Okay, so this is the key method for whether we can solve things or not. So the other variables are going to be independent variables as our inputs. Okay, these are the knowns or inputs. We'll often call them I.V, independent variables. Okay, for our mechanism, that's theta 2, our input. And to be able to solve this, we need our mechanism basically to have the mobility equal to our number of inputs. Right, for 4-bar, mobility equals 1. One input decides that. So number of independent variables equals mobility to be solvable. Okay, if you have a more a mechanism with mobility 2, like a 5-bar mechanism, you'd need to have multiple inputs to be able to calculate what's going on. Okay, so those aren't as common, although probably for your design projects, a lot of you are pursuing mechanisms which have, for example, 2 motors on it. And so one way to define that mechanism would be a mobility 2 mechanism, and you'd give 2 inputs, and you'd call those both independent variables. Okay, the other thing we're going to have is constants. Right, so every mechanism is going to have some constants, things that are not changing. Okay, for our mechanism, what is it? Theta 1? We knew that was 180 degrees. It's fixed. What else is constant? In this mechanism, all of the R values, the lengths of all those vectors, all those, we know they're constant. So we're going to put them in a separate list of constants, and those will not be independent or dependent variables. Okay, so your goal when doing analysis is basically, first, design your loop. So you're going to choose a loop that captures the motion. Then you're going to list your dependent and independent variables. You're going to assign them to one of these categories. If you know what they are right off the bat, you can call it a constant. And you're going to do this check. You're going to ask yourself, how many inputs do I have? Is that equal to my number of independent variables? If not, you can't solve it. Second, you're going to ask, is the number 2 of dependent variables, 2 dependent variables for each loop? We're going to look at a mechanism which has more complexity to it, more variables, and we're going to see that we need 2 loops to be able to solve it, where one loop will solve the first part of the motion, and that loop's output will become the input to the next loop. So that's going to be kind of a cool way of studying more complex mechanisms, but our loops are not going to get more complex than this. So next time we're going to actually express, let's say we have this loop equation up here. We're going to break this into 2 equations. This is the vector style, but we're going to write it out into 2 equations. Okay, and the power of this standardized vector definition is going to become clear when we do these, converting it from a vector into 2 equations like this, that each one of these looks identical. Cosine theta 3, sine theta 3. So all the x terms are going to be cosines, all the y terms are going to be sines. And you just need to worry about whether you have a plus sign or a negative sign. Okay, and on the output you have 0, which is a vector, so it's like 0 for both x and y. So this is 2 equations. I had to sneak it in here on 3 lines here. This is 2 equations. The first one is the x equation. And the second is the y equation, or horizontal components and vertical components. And so we can separate those. I've written them in this vector or matrix style here. But we can separate them. We can write one horizontal equation and one vertical equation. And we can just solve them as a simultaneous set of equations. So then it just becomes an algebra problem. Algebra and trigonometry solution problem. We can solve for anything we want. So let's say we wanted to find theta 4. It's just an algebraic problem now, and trigonometric problem. So we would solve it using techniques that you already know. We're going to go through that next time. And we're going to see, we run into some challenges sometimes, and then we'll see what we do with 2 loops after that. So that's all we're going to cover today. Have a great weekend, everyone. I'll see you next week.